Okay, welcome back. Let's get started. So last time we were in section 11.7, we were talking about um, critical points. We talked about implementing the second derivative test. And now we're going to be talking about, we want to find the absolute min and max on a closed region. So we have like a finite region here. So we're going to start with our little section on absolute max and min values on a closed bounded region. So first, a bounded and closed region is some set where all boundary points are included and every value is finite. So just some region where we also consider the boundary, and we can create an upper and lower bound for all of the elements inside of that set. So the extreme value theorem says if f is continuous on a closed bounded set that we'll call D in R2, then F attains an absolute maximum value at x1 and y1, and an absolute minimum value at x2, y2, at some points in D. So this basically just says if f is continuous and we have a closed bounded region in R2, then f 100% of the time achieves an absolute max and an absolute min. They exist. They have to exist. Now it might occur more than once. That's fine. You can still tie for an absolute max or an absolute min at more than one point, but it does achieve those values. So, steps. Step number one for doing a problem like this would be to find critical points of f in D and their values. So here we're testing the interior. The interior follows f, and all of those critical points could either be, mins, maxes, neither, but we're still going to have to plug in all those values to figure out what f at those points are. Now the next step is, because we have a boundary, critical points don't show up on the boundary unless both of the derivatives happen to be 0 along the boundary. But we still have to test them, because that might be where the absolute min and max is. So if you remember from Calc 1, when you did a problem like this, you'd always have to test the endpoints. Well, now we have all of the endpoints are the entire boundary. So we have to find extreme values of f on the boundary of D. So step 3 is just compare these guys. So we're going to find the largest and smallest of values from steps 1 and 2. So we've already gotten practice doing step 1. Let's do an example where we have this boundary and we're going to have to do this step 2. So our example is find the absolute max and min of the function 2 plus 2x plus 2y minus x squared minus y squared on the triangular plate bounded by x equals 0, y equals 0, and y is equal to 9 minus x. Okay. So why don't we sketch what this plate looks like? So we have our y and x plane here. And we're going along x is equal to 0, y is equal to 0. So we have the x and y axis, but then we also have the line y is equal to 9 minus x. So it starts maybe at a point up here, that's 0 and 9, and it ends up down here somewhere at a point 9, 0. And now we can do a straight line between these two. And then we also have the origin included here. So we have these 3 points make up our triangle. So we have x equals 0, y equals 0, and y is equal to 9 minus x. And we're considering everything in here, including the boundary. Okay. So step 1. We need to find all of the critical points in the interior. So we can do this just like how we've learned before. So we're going to take the first derivative. So we look at fx. This is 2 minus 2x. And we're going to look at fy. This is 2 minus 2y. So we need all of the points that make both of these 0. Well, the only time fx is 0 is if x is equal to 1. The only time that fy is equal to 0 is when y is equal to 1. So it looks like we only have one pair of critical points. And this is the point 1, 1. I also need to figure out what the value of f is here. So I'm going to go ahead and plug in 1, 1, and this is equal to 4. So notice I'm not doing the second derivative test. I don't care if this is a local min, a local max, or it's a saddle point. It doesn't matter to me. I'm trying to find the absolute max and min. So if at the end of the day, this is the largest value, then I know that it was a local max. And in fact, I know it's going to be the absolute max. So we're only interested in the absolute, not if this is local or not. Okay, so now we're going to move on to step 2. So step 1 is pretty easy. Step 2 can be a little bit lengthy because now what we have to do is along each of these segments, we're going to have to find extreme points. So maybe the function's, it comes up and then down along this line. I need to find the maximum along and the minimum along each of these boundaries. So the boundary is 3 lines. We need to test each one. There's no way around it. Each of these has a different definition of what makes up the curve. So we have to test each curve here. So I'm going to go ahead and look at the x equals 0 segment first. Oh, before we move on, I actually do want to note in step 1, the reason why we drew this first was we wanted to make sure that this critical point was actually in the domain. So the point 1, 1 is somewhere in here. So it is in our domain. I might be sneaky and have a critical point that's somewhere outside. If it's outside, don't care about it. We don't care. We move on. Okay. So now back to step 2. We're going to look at the x equals 0 case first. So along this line, x is equal to 0, x is equal to 0. So what I do is I just plug in that relationship. So x is in fact 0. So I'm going to plug in 0 for x into my function. And along this curve, my function looks like 2 plus 2y minus y squared. So now we have that this is how the function behaves along this line segment. How do we find the local extrema? Well, this is the Calc 1 way, right? We're going to go ahead, take a derivative, find out when it's equal to 0, and then test those points as well. So we don't notice that this is a function of only one variable now because we plugged in this curve. So you can take a total derivative. So we can do, so we're looking for the extrema. So we can go ahead and take a derivative of 2 plus 2y minus y squared. This just gives us 2 minus 2y. And we need to set this equal to 0. So basically what we're doing is we're finding the extrema along that curve. So here, this means that y is equal to 1. So I'm going to go ahead and test that point, which is still x is equal to 0, y is equal to 1. This is equal to 3. So we only have, why is it, oh, I did dx. Sorry, it should be a dy. There we go. Thank you. So we only have 2 points right now. We have 1, 1 and 0, 1. So right now, it looks like our candidates for the min and max are, this looks like the max, this looks like the min. But we're not done yet. We have to keep on compiling the list of all these points. Now, we're still not done with this line segment. Just like the Calc 1 case, we need to test the endpoints. Because on our line segment, we found x is equal to 0, y is equal to 1, maybe somewhere right here. But we still need to test those endpoints to see if they're larger or smaller than our critical point along that line. So we test the endpoints. The endpoints are at 0, 0, the origin. I plug that in and I get 2. I also need to test the other endpoint, which is at 0, 9. This is negative 61. Okay, so that looks like a good candidate. Do we also need to check if when y is equal to 0? Yeah, we're still on the x equals 0 case. We're going to do the y equals 0 and the y is equal to 9 minus x in a second. We're still on the same segment here. So now we've tested both of the endpoints of this line segment. So these are all still candidates. This looks like it's going to, right now it looks like our absolute min. But we're done with this segment now. So now let's move on to another segment. Let's do the y equals 0 case next. So here, I'm going to plug in the relationship into my function, which is that y is equal to 0. This gives me 2 plus 2x minus x squared. So I'm going to go through the same process. I'm going to find the extrema along this curve. Which is to say I can take an x derivative here. This just gives me 2 minus 2x. and I need this to be equal to 0. So that means that x is equal to 1. Okay, well, let's go ahead and plug in that point. Let's see what value it takes. So we plug in x is equal to 1, y is equal to 0. We plug that in and we get 3. Okay, so it doesn't look like it's our absolute min or max, but we had to check. Same thing with above. We also still need to check the endpoints. So the endpoints for this curve are the origin and 9, 0. So I know that we've already checked the 0, 0 endpoint, but just so we're consistent with treating each one separately, I'm going to go ahead and do it again. Of course, you don't need to do this, but I want to just, for sanity's sake, this is the endpoint for this curve. But the other endpoint we haven't tested yet, which is 9, 0. And this is negative 61. Huh, okay. So both of these have negative 61, 0, 9, and 9, 0. So they're both tied for being our absolute min so far. And once we're done checking the extrema along the boundary and the endpoints of that boundary, we can move on to the next line segment. So the final one to do is the y equals 9 minus x case. So you could solve for x and plug it into x, or you can leave it as is because it's already solved for y. So I'm going to plug that relationship into my function. So this is x 9 minus x. And if you did it the other way, if you solve for x, this would just become a function of y instead, and then you just take a y derivative instead of an x derivative. But we're going to go ahead and plug these in. This is a 2 plus 2x plus 9 minus x squared minus 9 minus x squared. So we can go ahead and simplify that. We can FOIL it out, and we'll get a negative 61 plus an 18x minus a 2x squared. Okay, so that's how the function behaves along this point here. Shouldn't it be a, oh yes, it is a 2. It is a 2 right here. Thank you. So there's a 2 times 9 minus x. Okay, so now the extrema are, so we take an x derivative. If you solved for x and you plugged it in here, then you would have a function of y. You can take a y derivative instead. But notice either way, we still have a function of only one variable. So we go ahead and take an x derivative. We end up with 18 minus 4x. We need this to be equal to 0. This means that x is equal to 9/2. And we have to plug this back into our relationship up here to find what y is at that point. So we go ahead and plug that in, and then we get that y is also equal to 9/2. So we can go ahead and test that point. So f at 9/2 and 9/2. This is negative 41 over 2. Okay, so just to be consistent, we're going to do the endpoints as well, even though both of the endpoints we've already tested in the above cases. Just for sanity's sake, we're going to do it again. So 0 and 9, which we got was negative 61. And we also had the endpoint 9, 0, which was negative 61 again. So that concludes our step 2. we've tested the extrema and the endpoints on every single one of these boundary elements. So step 3 is just the comparison of all these. So the max happens at 1, 1 with a value of 4, and the min happens at 0, 9 and 9, 0 with a value of -61. So we actually had that our global max happened inside of our region. So it's a good thing that we tested the interior. But we also had to note that our minimum occurred on the boundary. In fact, on the endpoints of our boundary. So it looked like all the way back up here that our max occurred at this 1, 1, and our min occurred at the little endpoints of our triangle here. So it's important that we tested all of the boundary here. Okay, so that concludes section 11.7. So we're going to be moving on to 11.8. So we're going to go ahead and start a new page here. So now we're going to talk about Lagrange multipliers. So Lagrange multiplier is a method for maximizing and minimizing a function. It doesn't need necessarily to be a function of 1, 2, 3 variables or so on. It's just, it is some function that's under a constraint. So we're maximizing, I should say, maximizing or minimizing a function. Maybe it's of 3 variables under a constraint of the form G is equal to some K, where K is a constant. So G is in fact a level surface in R4, right? We have X, Y, and Z is equal to some constant K. Okay. So what we're going to do is consider the problem of finding the point closest to the origin that's on our hyperbolic cylinder x squared minus z squared minus 1 is equal to 0. So we have some surface, and we want to know the point that's closest to the origin that is on this surface. So the function to minimize here that is not how you spell. Missed the, there we go. The function to minimize is the distance function. I want to find the distance from the origin to this point. So since it's from the origin, I have x minus 0 squared plus y minus 0 squared plus z minus 0 squared is equal to some distance squared. We'll move the square root over here to this d here because it's still a constant. So the constraint is that I have to be on my surface, which is detailed by x squared minus z squared minus 1 is equal to 0. Okay, so we can think of this guy as this expanding sphere. So let's have a little block of text kind of detailing what's really happening. We could plug in the relation of G, our constraint, into the function that we're trying to minimize, and find the global min but that's hard. We don't want to do that. So the whole goal of this is to implement this new method about when we have something to minimize or maximize, and it has to be subject to this constraint. We don't want to plug this constraint function into our function and see if we can find the min and maxes of that. So instead, imagine a small ball centered at the origin that's expanding until it touches the cylinder. So we have a ball centered at the origin, and it's continuously growing right until it touches the cylinder. And then we know that as soon as it touches the cylinder, that is the point that's closest to the origin. So each point where the ball and cylinder touch now have the same tangent plane. And normal line. So this gives us a way to kind of compare the ball's normal line and tangent plane to that of the cylinder as soon as they end up touching one another. So we should look at the level surfaces. So if I have that x squared plus y squared plus z squared is equal to d squared, I can set this to be my function of x, y, and z. And then I have my constraint function here, which is x squared minus z squared minus 1 is equal to 0. Actually, we need this guy to be minus and then equal to 0. So we'll set this whole thing here. It might not matter. I don't think it actually does, but I just want to be a little bit careful. So we have x squared minus z squared minus 1 equals 0 here. And then because g needs to be equal to some constant, our constant here is 0. We could have also moved over this 1. We'll have that g is x, y, and z. So now remember that the normal line of these guys is pointed in the direction of their gradients, right? So if they share a normal line, the gradient of f should be proportional to the gradient of g by some constant. And we call this constant lambda. So their normal lines are parallel with one another. They just might have a little bit different magnitude. So we just throw in this scale factor. This right here is our first kind of building block of using Lagrange multipliers. We don't have too much time left. We're going to finish this explanation tomorrow. I think Teddy is on now. Heather should be on shortly. You guys can have your 5-minute break. And then when they come back, you can start recitation. Yeah, this is as good as a place to stop before we start diving into the specifics.